6 disconnect rule allows a load center to operate without a main breaker provided that the number of disconnects, including the utility disconnect, does not exceed 6. If there is a ground fault downstream of any of the 4 breakers in the load center, the individual breaker that feeds the faulty subpanel should trip. This isolates the ground fault and prevents further issues. If a short to ground occurs on the main feeder, the power company's upstream protective devices will trip. This is because the fault will be detected by their equipment, designed to protect the grid from such events. The neutral and ground should only be bonded at one single point. This is usually located at the service panel or at the meter base. Bonding the neutral and ground at both the meter enclosure and the main load center is incorrect. It creates a hazardous situation by allowing potentially dangerous currents to flow through the grounding system. It is essential to have an electrician correct this issue. They should remove the bonding connection from the load center. Ensuring the electrical system complies with the National Electrical Code is important to ensure safe operation and prevent potential hazards. Bonding refers to the intentional electrical connection between the neutral conductor and the grounding conductor and is a critical aspect of electrical safety. The purpose of bonding is to provide a low impedance path for fault currents to return to the source. This allows overcurrent protection devices, like circuit breakers or fuses, to quickly trip and energize the circuit in the event of a ground fault. When a fault occurs, the current flows through the grounding system back to the source, and the low impedance of the bonding connection ensures that the voltage on the grounded metal parts remains close to 0 volts, minimizing the risk of electric shock. The National Electrical Code, or NEC, dictates the proper location for this bonding connection. The NEC mandates that the neutral and ground are only bonded at one point within a building's electrical system. This single point is typically located at the service entrance, which is where the power enters the building. This could be at the main service panel, the meter base, or an equipment grounding busbar in the service equipment. Having multiple bonding points can create parallel paths for neutral current, and this can lead to several problems. Firstly, it can cause unwanted current flow on the grounding conductors. Grounding conductors are intended to carry fault current only during a fault condition, not normal operating current. Secondly, circulating neutral current on the grounding conductors can create electromagnetic interference, or EMI, which can disrupt the operation of sensitive electronic equipment. Thirdly, multiple bonding points can increase the risk of electric shock. If the neutral conductor becomes disconnected or has a high resistance connection, the grounding system can become energized, creating a shock hazard. The 6 disconnect rule addresses the means of disconnecting all electrical power to a building or structure. This rule is in place to ensure that in the event of an emergency, such as a fire, all power can be quickly and safely disconnected by authorized personnel such as firefighters. According to the NEC, a building or structure must have a means to disconnect all ungrounded conductors from the service. This disconnecting means must be located at a readily accessible location, either inside or outside the building, nearest the point of entrance of the service conductors. The 6 disconnect rule permits the use of up to 6 switches or circuit breakers to serve as the main disconnecting means. This means that instead of having a single main breaker that disconnects all power, up to 6 individual switches or breakers can be used. The requirement is that all 6 disconnecting means must be grouped together in a single location. This grouping makes it easier for emergency responders to quickly disconnect all power to the building. This rule applies primarily to smaller buildings or structures where the electrical load is relatively low. In larger buildings with higher electrical loads, a single main disconnecting means is typically required. There are a few exceptions to the 6 disconnect rule. Firstly, if the building has emergency power systems, such as generators or uninterruptible power supplies, or UPSs, these systems must have their own disconnecting means that are separate from the 6 service disconnecting means. Secondly, if the building has fire pumps, the fire pump circuits must also have their own dedicated disconnecting means. Thirdly, if the building has multiple services, each service must have its own disconnecting means. The location of the disconnecting means must be clearly marked and readily accessible. This ensures that anyone who needs to disconnect the power can easily find and operate the disconnecting means. The disconnecting means must be suitable for the available fault current. Fault current is the amount of current that can flow during a short circuit or ground fault. The disconnecting means must be able to safely interrupt this fault current to prevent damage to equipment or injury to personnel. Ground faults are unintentional electrical connections between an ungrounded conductor and ground. These faults can occur due to damaged insulation, loose connections, or other factors. Ground faults can be dangerous because they can cause electrical shock, fires, and equipment damage. Ground fault protection is designed to detect and interrupt ground faults, and it is an important safety feature in electrical systems. There are several methods of ground fault protection. Firstly, ground fault circuit interrupters, or GFCIs, are used in residential and commercial applications to protect people from electric shock. Secondly, ground fault relays are used in industrial and commercial applications to protect equipment from damage. Thirdly, equipment grounding conductors, or EGs, provide a low impedance path for fault current to return to the source, which helps to trip over current protection devices. Ground fault circuit interrupters, or GFCIs, are designed to protect people from electric shock by detecting very small ground faults. GFCIs work by monitoring the current flowing in the hot and neutral conductors of a circuit. If there is a difference of more than a few milliamps between the current in the hot and neutral conductors, the GFCI will trip and interrupt the circuit. This difference in current indicates that some of the current is leaking to ground, which could be through a person's body. GFCIs are typically installed in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor locations. Ground fault relays are designed to protect equipment from damage by detecting ground faults. Ground fault relays work by monitoring the current flowing in the grounding conductor of a circuit. If there is a significant amount of current flowing in the grounding conductor, the ground fault relay will trip and interrupt the circuit. This indicates that there is a ground fault and that current is flowing through the grounding system. Ground fault relays are typically installed in industrial and commercial applications where there is a large amount of electrical equipment. Equipment grounding conductors, or EGs, are designed to provide a low impedance path for fault current to return to the source. EGC are typically made of copper or aluminum, and they are connected to the metal enclosures of electrical equipment and to the grounding electrode system. In the event of a ground fault, the fault current will flow through the EGC back to the source. This low impedance path helps to trip over current protection devices, such as circuit breakers or fuses, which will interrupt the circuit and prevent further damage or injury. The National Electrical Code, or NEC, provides detailed requirements for ground fault protection. These requirements vary depending on the application, such as residential, commercial, or industrial. The NEC also specifies the types of ground fault protection that are required in different locations. Ensuring that an electrical system has adequate ground fault protection is important for protecting people and equipment from the hazards of ground faults. Regular inspection and testing of ground fault protection devices is necessary to ensure that they are working properly. Understanding the electrical service is critical for ensuring the safety and reliability of electrical systems. The electrical service is the point at which the electrical utility provides power to a building or structure. It includes all the equipment and wiring necessary to deliver electricity from the utility's distribution system to the building's electrical system. The main components of an electrical service are the service drop or service lateral, the meter, the service disconnect, and the service panel. The service drop is the overhead wiring that runs from the utility's power lines to the building. The service lateral is the underground wiring that runs from the utility's power lines to the building. The meter measures the amount of electricity that the building consumes. The service disconnect is the main switch or circuit breaker that disconnects all power to the building. The service panel, also known as the load center or breaker box, distributes electricity to the various circuits in the building. The size of the electrical service depends on the electrical load of the building. The electrical load is the amount of electricity that the building is expected to use at any given time. The electrical load is determined by the number and size of the appliances, lighting, and other electrical equipment in the building. The National Electrical Code, or NEC, provides guidelines for calculating the electrical load of a building. The service entrance conductors are the wires that run from the service disconnect to the service panel. The size of the service entrance conductors must be adequate to carry the electrical load of the building. The NEC provides tables that specify the minimum size of service entrance conductors based on the electrical load. The grounding system is a critical part of the electrical service. The grounding system provides a path for fault current to return to the source, which helps to trip over current protection devices and prevent electric shock. The grounding system consists of the grounding electrode conductor, and the equipment grounding conductors. The grounding electrode is a metal rod, pipe, or plate that is buried in the ground. The grounding electrode conductor connects the grounding electrode to the service panel. The equipment grounding conductors connect the metal enclosures of electrical equipment to the grounding system. Bonding refers to the connection of all non-current carrying metal parts of the electrical system to the grounding system. This includes the metal enclosures of electrical equipment, metal conduit, and metal water pipes. Bonding ensures that all metal parts are at the same electrical potential, which reduces the risk of electric shock. The NEC provides detailed requirements for grounding and bonding electrical systems. These requirements are designed to ensure the safety and reliability of electrical systems. Regular inspection and testing of the electrical service is necessary to ensure that it is working properly. This includes checking the service entrance conductors, the grounding system, and the bonding connections. Any problems with the electrical service should be corrected by a qualified electrician. Short circuits are abnormal electrical conditions where current flows outside of the intended circuit path, typically due to a low resistance connection between 2 points of different potential. These faults can lead to a rapid increase in current flow, potentially causing damage to equipment, overheating, and even fires. There are several types of short circuits, including line-to-line faults, line-to-neutral faults, and line-to-ground faults. Line-to-line faults occur when two ungrounded conductors come into contact with each other. Line-to-neutral faults occur when an ungrounded conductor comes into contact with the neutral conductor. Line-to-ground faults occur when an ungrounded conductor comes into contact with a grounded surface, such as a metal enclosure or a grounding conductor. Short circuits can be caused by a variety of factors, including damaged insulation, loose connections, and accidental contact with conductive materials. When a short circuit occurs, the current flow increases dramatically, often exceeding the normal operating current of the circuit by hundreds or even thousands of amps. This high current flow can cause the wires to overheat, melt insulation, and potentially ignite surrounding materials. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from the damaging effects of short circuits. These devices are designed to trip or blow when the current exceeds a certain level, interrupting the flow of current and preventing further damage. Circuit breakers are resettable devices that trip when the current exceeds their rated capacity. Fuses are one-time devices that melt and break the circuit when the current exceeds their rated capacity. The interrupting rating of a circuit breaker or fuse is the maximum amount of current that it can safely interrupt. It is important to select overcurrent protection devices with an interrupting rating that is adequate for the available fault current at the point of installation. The available fault current is the amount of current that can flow during a short circuit at a particular point in the electrical system. This value depends on the impedance of the electrical source, the conductors, and any other components in the circuit. The National Electrical Code, or NEC, requires that overcurrent protection devices have an interrupting rating that is equal to or greater than the available fault current. This ensures that the device can safely interrupt a short circuit without failing or causing damage to the electrical system. Proper installation and maintenance of electrical wiring and equipment is important for preventing short circuits. This includes ensuring that all connections are tight and secure, that insulation is in good condition, and that equipment is properly grounded. Regular inspection of electrical systems can help to identify potential hazards and prevent short circuits from occurring. When a short circuit occurs, it is important to take immediate action to prevent further damage or injury. This includes turning off the power to the affected circuit, inspecting the wiring and equipment for damage, and repairing or replacing any damaged components. A qualified electrician should be consulted to perform any necessary repairs or inspection. The neutral conductor is a critical component of an electrical system, providing a return path for current to flow back to the source. In a typical alternating current or AC system, the neutral conductor is connected to the center tap of the transformer secondary winding. This creates a balanced system where the voltage between each ungrounded conductor, often called the hot wire, and the neutral conductor is equal. The neutral conductor is typically identified by a white or grey-colored insulation. The purpose of the neutral conductor is to carry the unbalanced current in a circuit. In a balanced three-phase system, the current flowing in each of the three ungrounded conductors should be equal, and the neutral conductor will carry very little current. However, in a single-phase system or in an unbalanced three-phase system, the current flowing in each of the ungrounded conductors may not be equal, and the neutral conductor will carry the difference in current. The size of the neutral conductor is typically the same as the size of the ungrounded conductors in a circuit. However, in some cases, the NEC allows for a reduced-size neutral conductor. This is permitted when the load is primarily nonlinear, such as electronic equipment, which can generate harmonic currents that flow primarily in the neutral conductor. The grounding system is separate from the neutral conductor. The grounding system provides a path for fault current to return to the source, which helps to trip over current protection devices and prevent electric shock. The grounding system consists of the grounding electrode, the grounding electrode conductor, and the equipment grounding conductors. The grounding electrode is a metal rod, pipe, or plate that is buried in the ground. The grounding electrode conductor connects the grounding electrode to the service panel. The equipment grounding conductors connect the metal enclosures of electrical equipment to the grounding system. Bonding refers to the connection of all non-current carrying metal parts of the electrical system to the grounding system. This includes the metal enclosures of electrical equipment, metal conduit, and metal water pipes. Bonding ensures that all metal parts are at the same electrical potential, which reduces the risk of electric shock. The NEC provides detailed requirements for the installation and sizing of neutral conductors and grounding systems. These requirements are designed to ensure the safety and reliability of electrical systems. Proper installation and maintenance of neutral conductors and grounding systems is essential for preventing electrical hazards. This includes ensuring that all connections are tight and secure, that conductors are properly sized, and that the grounding system is properly installed and maintained. Regular inspection of electrical systems can help to identify potential hazards and prevent electrical problems from occurring. The power company, also known as the utility company, is responsible for generating and distributing electricity to homes and businesses. The power company operates and maintains the power grid, which is a vast network of power plants, transmission lines, and distribution lines that deliver electricity to consumers. The power company is responsible for ensuring that electricity is delivered reliably and safely. The power company generates electricity using a variety of sources, including fossil fuels, nuclear power, hydroelectric power, and renewable energy sources. The electricity is then transmitted over high-voltage transmission lines to substations where it is stepped down to lower voltages for distribution to consumers. The power company is responsible for maintaining the transmission and distribution lines, as well as the substations and other equipment that make up the power grid. The power company is also responsible for metering electricity consumption and billing customers for their electricity usage. The power company monitors the power grid to ensure that it is operating safely and efficiently. The power company also responds to power outages and other emergencies. The power company is regulated by state and federal agencies. These agencies set rates for electricity and ensure that the power company is providing reliable and safe service. The power company invests heavily in infrastructure improvements to ensure that the power grid can meet the growing demand for electricity. The power company also promotes energy efficiency and conservation to help consumers reduce their electricity consumption.